Talk about training. That is for HMM, the model, which has A, B, and pi, where A would be the transition matrix, and B would be the emission probability for each of the state, and then pi being the initial state. So, so these would make up the parameters for the model, HMM model. The question is, how do we obtain A, B, and pi for a particular model? In other words, how do we perform the training? That is a given observation sequence. What we want to do is to determine HMM's parameter, which would be A, B, and pi. So this would be a problem of finding the model that maximizes the probability O, which is essentially the observation sequence, the probability of the observation sequence or the evaluation. Uh, so this would be actually considered as the counterpart to evaluation and decoding procedure, because for the evaluation and decoding, what you need would be the parameter. On the other hand, in order to obtain the model, you would perform the evaluation. Now, this is going to require a forward-backward algorithm, or also known as Baum-Walsh algorithm, which is supposed to be a hill climbing algorithm in the sense that we want to come out with a point where it maximizes the likelihood. And the way it is going to be done is that we in place an initial model, initial values of A, B, and pi, and using the forward-backward algorithm, iteratively re-estimates the parameters and improves the probability that given observations are generated by the new parameter. So this picture shows you the depiction of what is actually taking place. So this is actually EM procedure, expectation and maximization. We start off with an initial value of the parameter A, B, and pi. So with the initial, say, guessing or assumption, we start off and obtain the parameter estimation, which happens to be these. So these are transition probability, which is psi, and gamma, which would be the emission probability. So with these two, then we perform the maximization to obtain the specific transition probabilities or the transition matrix, as well as the emission probability, A and B, as well as pi. So once again, the hill climbing algorithm is essentially for obtaining what would be the model that maximizes this evaluation probability. So once again, we're going to go through each of these steps one by one. For example, obtaining the transition probability, psi t of I and j, as well as the emission probability, gammas of t of j, where once again, after going through the parameter estimation, and then which is actually the E step, and then the M step is going to then take the summing process, so that the transition probability would be obtained by sort of like integrating all of the transitions that has taken place over the observation from, say, t equal to 1 to t. Similarly, we do the same for the emission probability. So these are, so we're going to then, as I said, define and determine how the transition probability psi is made, as well as the emission probability, and then how they're going to actually translate them to the parameters that we need to by going through the M step, or a series of this EM step. Okay, so just to review of the probabilities with respect to the picture that we've had on the using the trellis diagram. On the forward probability, if you can recall, it was denoted by alpha sub t of I, which essentially is the probability of all the observation sequence up until t, right here, uh, for being in state, say, s of j, s of I at time t. In other words, the forward probability, alpha sub t of I, essentially is the probability of being in state s sub I given the partial observation from 1 to t. And similarly, the backward probability, which is denoted by beta sub t of I, would be essentially the probability, as you can see, the tail end from t plus 1 to capital T, given that you are at state I at time t. Once again, so this backward probability means that it is the probability of being in the state, say, I, given the partial observation in the tail end, t plus 1 to all the way to t, capital T. On the other hand, for the transition probability would be denoted by psi of sub t of I and j, which would be, as you can see, a joint probability of at time t being state, say I, 2, that at time t plus 1 state would be j, given the observation sequence as well as the model. So this would be the probability of going from state I to state j given the complete observation. So that would be the transition probability, which is, as you can see, designated as psi sub t of I and j. On the other hand, the state probability, which is related to the emission probability, is that denoted by gamma sub t of I, which is the probability of being at time t at state I given the observation as well as the model. So this would the probability of being in state, say, S of I given the complete observation. Now, I actually illustrated using these two pictures at the bottom here because they're related to, as you can see, the forward probability as being at, say, state, say, S of I at time t. So this means that at this particular node, which is, say, state I at time t, that would be denoted by alpha sub t of I, which would be the probability of all the observation sequence till OT, as you can see, being at, say, state I at t, right here. And similarly, for the backward probability, would be the probability of given at this particular node once again, denoted by beta sub t of I, would be to indicate that there would be the probability of the being in state, say, I at time t, so there will be probability of being in states, say, I, given the partial observations in the rear end, the tail end, from, say, t plus 1 to, say, OT. On the other hand, the transition probability here is denoted here or depicted here on the right side diagram, would be the probability of going from state I at time t to state j at time t plus 1 given the complete observation. So the observations is from 1, 2 to all the way till say O, say t minus 1 all the way to t. So that would be the transition probability. So this picture here does denote two nodes that are adjacent to each other, and in between, as you can see, that there is a probability of being from this node to this node being a sub I j, a sub I j times b sub j at time observation at t plus 1. Which this is going to be shown once again later on. I just want to say that for the transition probability, which is denoted by, say, psi sub t of ij, to mean that it is the probability going from state I at time t to state j at time t plus 1, given the complete observation. And for the state probability, which comes down to here in the first picture, would be, once again, that would be the probability of being in state, say, I at time t, given the complete observation, which is denoted by gamma sub t of I. So these two pictures at the bottom would be used to indicate, once again, the transition probability as well as the state probability, which is going to be shown in more detail. So once again, the training is going to involve EM procedure. That is, that we want to be able to obtain and find A, B, and pi, which are the parameters that make up the model, by maximizing the probability of the observation sequence. And the way it is going to be done is that we want to initialize the parameter first. And using that initialized parameter, we compute the model using this initialized parameter theta sub 0. So that model is going to be done by this E step, where the E step is going to involve obtaining or finding the transition probability chi sub t of ij, as well as gamma sub t of I. And then we take the M step, where the M step is going to involve having the three parameters being re-estimated. The initial state distribution, the transition probability A sub ij, as well as the emission probability B sub j of Vk, which for the transition probability, it's going to involve the individual psi t of ij, whereas for the emission probability, it's going to involve the gamma sub t of j. So this process is going to be repeated again and again until the changes in the observation probability does not occur, does not happen. In other words, the difference between the previous observation sequence probability to that of the current observation sequence probability is about the same. That's when the convergence has taken place, and that's when we stop the training. So this training model is also called the Baum-Walsh algorithm, and it's, as you can see, is an EM algorithm, where in this step, as I said, the E step would involve calculation of the transition probability, psi of t of ij, as well as the state emission probability, gamma sub t of I. So now there are some couple of practical issues. That is that this EM algorithm can actually get stuck in a local minima or local maxima as well. And there could be some also numerical problem having to do with the log and the scaling, which is actually is not really that important at this point. I think more important is to get you understand how these the training, the bound Welch algorithm actually becomes involved in terms of obtaining once again the transition probabilities as well as the state probability or emission probability. So the uh, the the uses of the maximum likelihood estimation of the parameters is going to actually allow us to be able to obtain the transition probability, which would be essentially a ratio between the number of transitions from state Si to state J divided by the number of transitions out of state, say, I. For the emission probability, uh, it would be the ratio of the number of times observation V sub k occurs in state, say, S of I, um, over or divided by the number of times in state S of I. And similarly, for the initial probability, that would be the expected frequency in state, say, S of I at time t equals 1. Okay, so now let's delve into the specifics. So what we want to do is to define variable psi sub t of ij as the probability of being in state S of I at time t and in state S of j at time t plus 1, given the observation sequence, the entire observation sequence, that is. So mathematically, that psi of t ij would be described or expressed by this, which is the, as you can see, the joint probability of, say, state I at time t to that of state j at time t plus 1, given the entire observation sequence. Now, this is going to be equal to, um, as you can see, the probability of the joint having the observation sequence involved here in the numerator, divided by the probability of the observation sequence. So this is actually, as you can see, the joint probability versus that of the conditional probability. If you will, the probability, say, A and B would be then equal to probability of, say A, let me rewrite this. So the probability of A given B would be equal to the probability of A and B divided by probability of B is what we have. So for example, this would be, say, B, and so this would be, say, A and B, and this would be A. So you can actually see clearly that you can actually make a joint probability in the numerator, and you can divide by the condition, which happens to be the observation sequence. Now, this in return, the numerator, as you can see, is a joint probability among the state being, say, I at time t to that of state being j at time plus t plus 1, as well as the observation sequence. Now, this is going to be, which is going to be shown later on. But I just want to say that this is going to be then equal to uh, product of, as you can see, the state I at time t with a partial observation of say 1 to say small t, and then it is multiplied by, as you can see, the probability of the partial observation sequence from t plus 2 to say capital T, given that at time t plus 1, the state is j. And then also it is multiplied by a transition probability A sub ij to that of B sub j at observation, say, t plus 1. And then the denominator is the same, as you can see. And the numerator is going to be the length numerator is going to actually be, as you can see, simplified to, if you can recognize that the first term here, the first term is actually the dynamic programming's alpha sub t of I, which is the forward uh, algorithm. And then the last term here is the beta sub t plus 1 of j, which is the backward algorithm. And then we have the in-between, alpha sub, A sub ij, the transition probability, as well as the emission probability at, say, state j, with the observation being at t plus 1. And then the um, denominator here would be actually same as this, which happens to be essentially double summing over inj of the numerator, because when you do the double summing over inj, that gets rid of all of the state I and state j, the possibilities of state I and state j, and that's going to just leave the observation sequence, the probability of the observation sequence. In other words, this is the same as the probability of observation sequence. So this is what I want to show with the Baum-Welch algorithm on the expectation step. Now, before we really delve into the the specifics of the expectation step of the EM algorithm, we can do the re-estimation using the transition probability that we have just obtained into A sub ij, where that A sub ij, as I said before, would be the ratio between the expected number of transitions from state I to state j divided by the expected number of transitions out of state I, which can be then computed by, for the numerator, the expected number of transitions from state I to state j would be essentially the sum of taking all of these state transition probability from, say, from t equal to 1 to capital T minus 1. In other words, you sum all, you do this for all of the time sequence. And similarly, for the denominator, you would do the same over all of the time, and especially for the transitions out of state I, so you would sum all of the j's. So as far as the numerator intuition is concerned, this is numerator intuition concerned, what it essentially means that if we knew, assuming that we had some estimate of the probability that a given transition I to j was taken at time t in observation sequence, then if we knew this probability for each time t, we could sum over all t to get the expected value. In other words, the number of count for I to j. Okay, so let's delve into a little bit more detail of how this estimation A sub ij becomes, as was denoted here at the previous slide. So to begin with, what I want to do is to define, once again, psi sub t which is the probability of being in state I at time t and state j at time t plus 1, given the entire observation sequence as well as the model. So this psi sub t of ij would be the transition probability from, say, state I to state j at time t to that of time t plus 1, given, once again, the entire observation sequence and the model. Now, with this, what I want to now at this point do is to compute actually this transition probability from another very similar term called not quite psi. Not quite psi is defined by this, which is actually very similar, but this is actually the joint probability of the state being I at time t to that of state being j at time t plus 1, as well as the observation sequence. So this is joint probability, having the observation sequence as part of the joint variables given the parameter. So I should say that what this not quite psi is that this observation is now moved toward as part of the joint variable. Now, with that not quite psi t of ij, which once again sort of like moved the observation sequence as part of the joint variable. It's going to then have essentially 4 components to describe this. The 4 components are the alpha, the forward algorithm, the beta, the backward algorithm, and A sub ij, which is the transition probability, as well as B sub j OT, which happens to be the emission probability at state j at time t. So that's actually depicted here in this trellis diagram. That is, say at being, say state I at time t. So this is going to actually have the observation sequence observed from t, say OT, O1, all the way to say t, and being at, say, state I at time t. So that would be essentially the forward algorithm, which is described by alpha sub t of I, which is, once again, is the probability of the observation sequence from 1 to t, and being at, say, state I at time t. So this would be then is going to be involved for computation of this not quite psi, which is going to be shown later on. Now, at the same time, being at, say, state j at time t plus 1, this is going to be actually used to describe the backward algorithm, beta sub t plus 1 of j. So beta sub t plus 1 of j means that being at a state, say S of j, being at state j at time t plus 1, which is right here, t plus 1, it would be the observation, it would be the probability of the tail end observation sequence. That is from, say, t plus 2 to t plus 3 all the way to o, say, t. So this is what that means. So we have indicated 2 state probabilities with the observation sequence. One being, once again, at this state, being, say, I at time t, which having these observation sequence, which is then computed by alpha sub t of I, as well as being, say, at this j, state j, at time t plus 1, being essentially computed by the backward algorithm, which is beta sub t plus 1 of j, which is, once again, with the probability of the observation sequence starting from, say, t plus 2 all the way to capital T, given given that you are here at, say, state j at time t plus 1. And in between, say, state I and j, where state I is at time t and the state j is at time t plus 1, the in between would be described as this in between h would be described as the transition probability between say I and j. So that would be a sub ij multiplied by being at this state. So that would be the emission probability at, say, state j at time t plus 1. So this is how this not quite psi t of ij can be computed. That is, we want the psi of t of ij being the joint probability of state being, say, I at time t being, say, state j at time t plus 1. In other words, state transition being from I to j conditioned on the observation sequence and the model. But now, however, we've got not quite psi ij, where this observation sequence is now part of this joint variable. Now, this, once again, as shown by the previous slide, can be computed as the products of alpha sub I ti multiplied by the beta sub t plus 1 of j, which is the backward algorithm. This is the forward algorithm. And then it is multiplied by a sub ij as well as b sub j of o t plus 1. So the entire product represents this probability where there is a transition between I to j at time t to t plus 1, as well as the entire observation sequence. So once again, alpha sub t of I represents the partial sequence observations from, say, the front end, whereas the beta represents the observation sequence of the probability in the rear end or the tail end, and then a sub ij times b sub j at o t plus 1, these two represents the edge between, say, state I to state j, where I is at, say, time t, and state j is at, say, at t plus 1. So once again, we essentially won the state transition probability. So that is psi sub t of ij, which is defined or expressed by the probability of the state transition, that is state being I at time t to that of state of j being at time t plus 1, given the entire observation sequence and the model. On the other hand, we have the not quite psi sub t of ij being the observation sequence being among the joint variable, which has moved from the conditions to part of the joint variable. Now, we also realize that with the say y being part of the condition, this can be described by the probability of the joint x and y divided by the probability of y. So therefore, what we need in order to make this happen is to divide the not quite, this one here, by the probability of the observation sequence. So in order to obtain this, the transition probability, all we need to do is to put this thing up here in the numerator, and then you divide it by the probability of the observation sequence. So once again, cosine sub t of ij is a ratio of not quite the cosine sub t of ij, and it is divided by the probability of the observation sequence. And we saw that the not quite cosine sub t of ij is essentially the product of the forward algorithm, alpha sub t of I, times the backward algorithm, beta sub t plus 1 of j, and then the h between state I and state j, which happens to be a sub ij times beta sub j, sorry, b sub j of t plus 1. And turns out that the denominator, which is the observation sequence, can be actually obtained by both either the forward or the backward algorithm. So in this case, if we just use the forward algorithm, we can say that this is this not quite, and then the denominator which is the probability of the observation sequence. We can just use, say, alpha sub capital T. Okay, now, so with that, with the expectation part, we now perform the maximization part, which is the estimation or re-estimation of the A sub ij from the cosine. So A sub ij, the actual re-estimation of the transition probability would be the ratio of the expected number of transitions from state I to state j divided by the expected number of transitions from state I. So this means that the expected number of transitions from state I to state j is the sum over all t, the time of the cosine. So all you need to do is just sum of over all of the cosine over time. And then the total expected number of transitions out of state I is the sum over all transitions out of state I. So in other words, all you need to do is that we sum over all t, just like here in the numerator, as well as we sum over all j, because they are the number of the transitions out of state I. So this is how we obtain A sub ij estimate, or the re-estimate of the transition probability. So the final formula for the re-estimated A sub ij would be this. Now, what about the re-estimating the observation likelihood B? So this is the probability of a given symbol, nu sub k, from the observation vocabulary given, say, state j, which is indicated by B sub j of Vk. So in other words, B sub j of Vk is the ratio between the expected number of times in state j and observing a symbol V sub k divided by the expected number of times in state j. Now, we then need to know the gamma sub t of j, which happens to be the probability of being at state j at time t given the observation sequence as well as the model. Now this one here can be also described as, just like the way we've done it for the transition probability, is to put the observation as part of the joint probability. So at the numerator, it would be the probability of the state being j at time t, along with, joint with, the observation sequence, and then it is divided by the probability of the observation sequence. Now, this particular element here, the numerator, which is the probability of state being at j at time t, as well as the entire observation sequence, is essentially forward algorithm times that of the backward algorithm. That is alpha sub t at j times beta sub t at j, which this means that both together it takes care of both the partial observation from 1 to say small t, as well as uh, the tail end, the partial tail end observation sequence. So together they make up the entire observation sequence, and together being at a state say j at time t, and the uh, denominator is still the probability of the observation sequence. And this gamma sub t of j, which is the probability of being in state j at time t, that can be used to obtain, once again, the expected number of times in state j and observing symbol v sub k would be to take all of the state probability being, say, at state j at time t, as well as for the state having the observations of, say, v sub k only. So that would be the expected number of state j and observing symbol v sub k. And then you divide by the expected number of times in state j, which would be just summing over all of the t of the gamma, where t is from 1 to capital T. So we're essentially summing of all of these the probability of being in state j at time t, and we sum over all time would be what this is, or what this is. Uh, sorry, what this is right here. Okay, so that process is actually depicted here in this slide. So once again, computing the gamma of, say, sub t of j would be the probability of being state j at time t, given the observation sequence and the model. So this can be re-expressed as the joint probability of the state being at j at time t, as well as observation sequence, and then you divide by the probability of the observation sequence. Now, the numerator, once again, being, let's say, at this state j at time t. So this would be, this here could be expressed as you can see, alpha sub t of j would be the front end, and the beta sub t of j would be the real end, and together they make up the entire observation sequence, as well as being at state j at time t. So therefore, the numerator is essentially just the product between the alpha sub t of j to that of the backward beta sub t of j, and then the denominator would be the same, which is the probability of the observation sequence. Okay, so in summary, the alpha sub ij would be the ratio between the expected number of transitions from state I to j and the expected number of all transitions from state I. So by obtaining the psi sub t of ij, the numerator is just summing over all time, and for the denominator, you're summing over all time as well as summing over all j. So that will be the transition probability, and the emission probability being as, say, state j and observing, say, k observation would be that you sum over all the gamma over t, but only those with observation having v sub k for the numerator, and then you divide by this summing over all the gammas over time. So this is the ratio between the expected number of times the observation data emitted from state J would be v sub k, and the expected number of times any observation is emitted from state J, which would be this denominator. Okay, so the bound-Welch algorithm maximization step is to obtain A sub ij by having this ratio, where each of these psi sub t is obtained by this ratio. And the emission probability B sub I Vk would be obtained by this ratio, where inside of this there's a gamma which is obtained by this ratio. And the initial probability actually can be also obtained by the gamma, because gamma essentially represents the probability being at, say, gamma sub t of j essentially means that it's the probability being at state j at time t. And so for pi sub I would mean that it would be actually gamma sub 1 at I. So you could actually use the gamma to be able to obtain the pi sub I, which is the initial probability. Okay, so this slide actually tries to show the overall process, the expected the expectation step, where in the expectation step you obtain the state probability, state at j or I at time t probability, as well as the transition probability size of t of ij, where both of the state probability and the transition probability can be obtained by using the forward probability as well as the backward probability. And so this actually is a continuation of the previous slide, just to be a little bit more detail, and sort of like showing you the in-between procedures. For instance, this size of ij would be a ratio between the probability of being these state changes from, say, I to j, as well as jointly with the observation sequence, divided by the probability of the observation sequence, where the numerator, once again, would be then equal to alpha sub t of I times the beta sub t of j, and then the edges, which would be A sub ij times B sub, say, j, at say, observation being t plus 1. So the training is, once again, that it involves the E step as well as the M step. The E step would be obtaining the state probability as well as the transition probability. For the M step is the re-estimation of A sub ij using the psi, and B sub j, the emission probability, using the state probability. And we do this again and again until A and B, or the probability of the observation sequence no longer changes. Okay, so there are lots of resources for HMM, as well as including some simulations. So here are some of the resources for you. For example, HMM Toolbox provided by Kevin Murphy, as well as other resources as well. Here's another resource for HMM simulation. And here in the appendix, I've included some of the example applications of HMM. including that of speech, with some code, as well as here's some code for the speech, as well as gesture, uh, and there's also code for gesture as well in the back. So I'm not going to go in detail. I think the code can be self-explanatory. If you can just say copy and paste and then just run it. They're all in MATLAB, so MATLAB code. Okay, so that's what I have in mind for the HMM, hidden markup model.